So let me give you an example, okay? So the example here is actually the simplest example in finite element people actually use. So first of all, let's figure out what metric should we optimize to solve the Poisson's equation. To solve the, let's just do 1D Poisson's equation. This plus f equal to 0. So second derivative of w plus a certain function has to equal to 0. And it has been a long time before since people figured out if you want to solve this equation. And there is actually a lot of physical intuition behind this. It is equivalent to minimization of the total energy. So the minimization of an integral, let's say from 0 to 1. Let's say w equal to 0 at x equal to 0 or 1. Okay. If I have this boundary condition and the Poisson's equation, it is equivalent of minimizing dw dx squared minus f times w dx. All right. Well, why is that? I mean, this step is maybe the less trivial ingredients of finite element. Is how do you go between a differential equation and the minimization of some global metric? And the correct tool to use for this is a variational analysis. It's like analysis of variations. So for example, in this case, we can basically take a small variation of the function w and find out why the minimizer of this metric is actually satisfying the differential equation. So for example, if I define E to be like this, then a small variation in E caused by a small change in w, right? So imagine you change w a little bit, okay? If you change w to w plus an infinitesimal delta w, then the resulting change, infinitesimal change in E is going to be actually 2 times dw dx times d delta w dx, right? It's the same as taking derivatives, minus f times delta w dx. Right? Okay, I get a factor of 2 here, so I must be missing divide by 2 over here, right? Usually you have kinetic energy being like half of v squared or something like that. I mean, that's where it appears. So if I take derivative, so now if I define the energy to be this thing divided by 2, now when I take a variation, I got rid of the divide by 2, right? Okay, so now the next step is integration by parts, because I want to, the criterion for being optimal, having optimal E, minimum E, is that no matter how I change my W, right, my E would not change to first order. It's like we just said in deriving the Goodenough scheme, the criterion for the derivative of the function being 0 is actually when it achieves minimum or maximum. Same thing here, generalized to analysis of variations, saying the criterion for being maximum or the necessary condition for being minimum or maximum is that when you take a first order variation, the first order variation is equal to 0, no matter what delta W is. So the no matter what delta W is has to be taken into account by moving this delta W from within the derivative to out of the derivative. So if we do that, we use integration by parts on this one. We first get a negative sign. So let's figure out the boundary condition, boundary term first. So as you know, if I have a function a times db dx, integrate over 0 and 1 is equal to a times b, the difference between a times b in 0 and 1 minus integration of dA dx times b, right? So that's integrated by parts. How many people are not familiar with that? No? Okay. So basically this is the reason we have this is if you combine these two terms, right? dB dx times a plus b times dA dx is actually equal to dA times b dx, right? So you integrate over this over 0 and 1, you get this. So that's kind of the standard formula to use for integrating by parts. So in here, this is my a, and the delta w is my b. Okay, so if you follow the logic, a times b is dw dx times delta w over 0, 1. So that's this term. The other term is integration of 0 to 1. Now I'm taking derivative to a, which is already a derivative. So I get a second order derivative with respect to w and times delta w, integrate over delta x. And I don't want to forget the other term, integration from 0 to 1, f delta w dx. All right? Okay, and now I want to use my boundary condition. So I already know w equal to 0. So when I'm taking a small variation, my delta w cannot be anything but 0 at the boundaries. So this is going to be gone, right? Because delta w is already 0. So what I got remaining is minus integration 0 to 1. So these two terms can combine each other. They all have a delta w in common. d squared w dx squared plus f dx would be equal to 0. So now for the delta E to be 0 for any delta w, d squared w dx squared plus f has to be 0. Therefore, we get the Poisson's equation. Okay, this whole analysis is a little bit non-trivial, but the goal is always the same for any differential equation, is to convert the differential equation into a metric you minimize, so that when you minimize that metric, you get the solution of the differential equation. Okay, once you do that, once you have that metric, go back to finite elements, right? Go back to finite elements. I'm going to be minimizing that metric under some constraints, under some additional artificially imposed constraints, so that I get finite degrees of freedoms. That's it, right? And the mechanism of finite elements, there are really two components. One component is to basically take the differential equation, how do I systematically get a metric I can minimize? And as we are going to see later, many forms of finite element doesn't even require you to go all the way to that metric. You can go halfway to a variational form like this. So this variational form is saying that, okay, I take a variation of the metric, the variation has to be equal to 0. Right? So if I have a metric to optimize, I'm sure I can get a variational form. But there could be variational forms where it does not correspond to the optimality of some integral metric. Right? So basically finite element only requires you to have a variational form like this. It doesn't require all the way for me to get a metric. But like if I do have a metric to minimize, I can prove a lot more interesting things for finite element. So let's actually discuss finite element under the existence of such metrics. But like the first part is how do you go between differential equations and the metric for different boundary conditions, different derivative terms, and things like that. Okay. The second part of finite element is how do you construct these constrained functions so that you only have finite degrees of freedoms, and how do you play with the finite degrees of freedoms to minimize that metric. So that's the two parts we are going to learn in finite elements. So hopefully today I'm giving you kind of a brief overview of what finite element is. All right, so I will see you, next week I don't think we have any lectures. It's, right? It's a...
No class Monday or Wednesday.
Yeah, no class Monday or Wednesday. I think I'm not here on Wednesday, so I think we are canceling the class and move it to another day, another Friday, right? So, but the project is still going to be due. So, yeah, I'll see you in a bit less than 2 weeks.